Hi everyone, welcome to our webinar this week. So coming with us today is our speaker Bruno Lourenço from the he's a associate professor at the Institute of Statistical Mathematics, Department of Statistical Inference and Mathematics. Prior to that, he's an assistant professor at the University of Tokyo and also assistant professor at Seikei University. He got his PhD at the Tokyo Institute of Technology, Japan, in mathematical and computing science. So it's a very great pleasure to have him here present to us about error-bound amenable con and beyond. So please, now is your stage.
Thank you. First, thank you very much for the kind introduction. I'm very happy to present at this seminar. So I'd like also to thank all the organizers for this very kind invitation. So today I'm going to talk about error bounds, amenable cons, and beyond. So if you have any question at any moment, please feel free to interrupt me. So, I'm mainly interested in this talk. I'll be mainly interested in conic linear programming. So in conic linear programming, what you have is you want to minimize some linear function subject to the intersection of the form L plus A intersected with some con K. So here L is a subspace contained in some space, and A and C are vectors in this space. So this is what's called a conic linear program. So the general philosophy behind this kind of optimization problem is that we try as much as possible to isolate the nonlinearity of the problem inside the conic part. And there are a few reasons why one might want to do so. One reason is that you have many good solvers for solving this kind of problem. So you have some classical solvers like Sedumi, STPK3, STPA, and you also have the Mosaic solver, which can also solve problems in this form. This one is a commercial one, but it's free to use in the academia. You can get free academic licenses. So if you are able to solve, if you're able to put your problem in this form, you can use some very good solvers. And this creates a kind of a cycle. So you have good solvers for this problem. So this motivates people to find ways of making their problems fit inside these frameworks. And one book that, for example, that shows some of these applications is these lectures on model convex optimization by Bental and Emirovsky. And you can also see some of the modeling examples in Mosaic's cookbook. This is also a very nice material. So if you are more or less convinced about the importance of taking a look at this problem, then I suppose you'll be more or less convinced about the importance of looking at this very closely related problem, which is the conic feasibility problem associated to this problem. So here we simply want to find a point X that belongs to this intersection. And as a reminder here, K is a closed convex cone, L is a subspace, A is a vector, so that L plus A is an affine space. Now, of course, you can study this problem from many different points of view. And here, I'll mention some of the results I've obtained on error bounds for this kind of problems. And as I progress in my talk, I'll also mention some of the results I've obtained with my co-authors. So the main problem we are interested here is this one. So suppose you fix some norm on your space and you pick some vector. Then you can naturally think about three different quantities. You can think about the distance between X and the affine space. You can think about the distance between X and the cone, and the distance between X and the intersection of these two sets. Then a very natural question is this: how can we use the individual distances to say something about the distance to the intersection? So this is essentially a question about error bounds. And the reason why, well, I think there are many reasons why people are interested in this kind of question, but a very clear application of this is in convergence analysis. So if you had, say, if you think about, for example, alternating projections, where you first project in one set and then you project into another set, it's natural to want to know how close are you getting to the intersection when the individual distances decrease. So this kind of study helps on, for example, on this kind of convergence analysis. And this example is actually a relatively favorable case where you have the intersection of two half lines. But still, in this still relatively favorable case, you can still see that it can be the case that X is very close to these two sets, but still it is relatively far from the intersection. Oops. Now, so this is essentially I'm essentially talking about error bounds. So let me first give an example of the kind of error bound we are interested. So here, more generally, suppose I have two closed convex sets, C1 and C2, and I denote their intersection by C. We say that they satisfy a Hoderian error bound if for every bounded set you have two constants, this constant theta b, and so some gamma b, which I'll call this an exponent, such that you can upper bound the distance to the intersection by some quantity that depends on the individual distances. But you have to take into consideration this exponent here. If it happens that this exponent does not depend on the bounded set, we say that this error bound is uniform. And if the bound is uniform with gamma equal to 1, we have what's called a Lipschitzian error bound. So let me show you a few known results on this. Now, again, here C1 and C2 are convex sets. And it's well known that if their relative interiors intersect, then you have a Lipschitzian error bound. I'm actually not very sure who was the first, or who was the first person to prove this result. But you can find, for example, this in a paper by Bauschke, Bowen, and Lee, and also a proof in a paper by Beck and Tebould. And when you have a Lipschitzian error bound, this also goes by some other names in the literature. So sometimes this is also called bounded linear regularity. And a very nice example when you also have a Lipschitzian error bound is when both sets are polyhedral. So this is a result that's known by Hoffman's lemma. But in fact, Hoffman's lemma is much stronger than what I'm saying here. In the case of Hoffman's lemma, not only is the exponent equal to 1, but the constant can be taken in such a way that does not depend on the set B. And you also have more recent results. So this is a result by Bowai, Goin Li, and Yao that says that if you have basic convex semi-algebraic sets, then you also have a uniform Honderian error bound. And you also have a result by Stum that says that if C1 is an affine space and C2 is the cone of positive semi-definite matrices, then you have a uniform Honderian error bound. So I'm going to discuss this in more detail in the next slide. But a key point is this. I don't want to know, I mean, not only I want to know that a Honderian error bound holds, but if a Honderian error bound holds, I would like to be able to compute the exponent as tightly as possible. That is one of the goals. So let us take a look at Stum's error bound. So Stum proved the following. Suppose you have an affine space that intersects the cone of positive semi-definite matrices. Then there exists some gamma, some non-negative gamma, such that whenever you fix some ball of radius rho, for the guys inside this ball, you can find this constant kappa rho, such that whenever your point is close to each one of these sets, you can upper bound the distance to the intersection by this quantity. So you have essentially you have a Honderian error bound, and the exponent is given to 2 to the power minus gamma. And the surprising thing about this result is that it is tight, meaning that you can find a particular instance of a affine space for which you cannot do better than a Honderian error bound with this gamma equal to n minus 1. And Stum also showed in his paper how to compute this exponent for an arbitrary instance. So if you are given, if you are given a concrete affine space, there is a way of computing this exponent. And this is connected to facial reduction and something called the singularity degree. And I was very inspired by this result. So what I set out to try to do is to see for which kind of cones can we obtain a result similar to what Stum proved. So what I found out was that for symmetric cones, a result very similar to Stum's error bound holds. And actually, for symmetric cone, a result almost identical to Stum error bound holds. And if your underlying cone is the so-called amenable cone, then you can get some results that have a similar flavor. And for that, we need 3 ingredients. We need amenable cones, facial residual functions, and facial reduction. So from now on, I'm going to explain each one of these 3 ingredients in succession. Okay, so first, So first, let me talk a bit about amenable cones. But before that, just a very brief review about faces. So if you have K a closed convex cone, and F another closed convex cone containing K, we say that F is a face if whenever you pick two elements that belong to K and their sum lies in F, then they must already be in F. And you have that F is an exposed face if it is exposed by some supporting hyperplane of the cone. So in essence, if you can write this face as the intersection of K with this hyperplane Z, with Z coming from the dual cone. So F can be expressed as K intersected with some supporting hyperplane. An important fact is that no matter whether the face is exposed or not, this inequality always holds. So if you pick the span of the face intersect with the cone, you recover the face. And here's an example. So you have, this is an ice cream cone cut in half. So all of these are faces. So you have this orange face, and you have infinitely many one-dimensional faces running along the boundary. You have the whole cone is also a face, and the origin is also a face. With that, we say that a cone is amenable if for every face of F, or every face of K, there exists some constant such that you can upper bound the distance to that face by the distance to the cone times some constant. And this holds for every X in the span of F. Just a moment. Having some slightly technical issues. So as a reminder, we always have this inequality. So this, we always have this characterization here. F is always equal to the span of F intersected with K. So it turns out that this is the same thing as saying that span of F and K have a Lipschitz error bound, or that they are bounded linear regular. Now, this is a sort of non-trivial property for a cone to have, because typically when the face is proper, when the face is not the whole cone, the span of F does not intersect the relative interior of the cone. So this kind of property does not follow, for example, from any of those criteria. So a natural question is, what kind of cone does satisfy this property? Well, it turns out that all the symmetric cones, which include, for example, the cone of quasi-semi-definite matrices, are amenable. And in particular, in the case of the symmetric cones, the constant can be taken to 1. All the polyhedral cones are amenable. Also, all the strictly convex cones are amenable. And this property is preserved under linear isomorphism in direct product. So if you take direct products of amenable cones, this is also amenable. And if two cones are isomorphic, and one is amenable, the other must be amenable. So this was what I knew about this thing, about these objects, by the time I wrote the amenable cones paper. But I've been working with Vera and James, and we figured out a few more things about this class of cones. First is that a class much larger than symmetric cones are amenable. So all the hyperbolistic cones and all the spectrahedral cones are amenable. I'm not going to explain what's a hyperbolistic cone, but the spectrahedral cone are the cones for which you can obtain as slices of the positive semi-definite cone. And amenability is also preserved by intersections and by slicing. So if you have an amenable cone and you slice it, for example, by some hyperplane, you get some convex set. And there is a special way of defining amenability for convex sets. Here, I only define for cone, but there is a way of defining this for convex set. And if you do so, you get that amenability is preserved by any slice by a hyperplane. And if you construct a cone from amenable compact convex set, it's also amenable. So these results are described in these two papers. Another few things we were able to prove recently is this. So first, let me explain very briefly what is known. So there are several facial exposedness properties that a cone might have. I already mentioned facial exposedness. And amenability, it is sandwiched between two other properties. So there is something called nice cones and projectionally exposed cones. So amenability sits sandwiched between these two classes of cones. And in fact, if the dimension of the cone is less than 3, all these notions are the same. But we reconstructed a 4D cone that is facially exposed, but not nice. And what we worked a bit on these things. And what we figured out was that there exists a 4D cone that is nice, but not amenable. So you can find nice cones that are not amenable. But in dimension 4 or less, these two things are the same. So if I suspect that there exist amenable cones that are not projectionally exposed. But if you want to find them, you have to look at least in dimension 5. So for the moment, that's more or less what I wanted to say about amenable cones. Are there any questions so far? So if not, let me continue a bit more. So I already talked about amenable cones. Now I'm going to explain the second ingredient we need in order to get error bounds, which is the notion of facial residual function. So suppose we have K, a closed convex pointed cone, F a face, and Z an element of the dual cone of that face. Now, this is a fact from convex analysis that the intersection between F and Z pub is equal to this. And this is just because, as I mentioned before, this part here is equal to F. So this implies that if the distance between X and K is 0, the distance between X and span of F is 0, and X is orthogonal to Z, then the distance between X and the intersection is 0. So the distance being 0 just means that the point is inside the set. So this is always true, no matter what's the situation. So a natural question is, if instead of this distance being 0, if instead these quantities are only less or equal than epsilon, what can we say about this distance? And the problem is that in general, this quantity will not depend on epsilon only. You also need to take into account the normal effects. Nevertheless, the facial residual function is the object that provides an answer for this question. So a facial residual function is a function that has some monotonicity properties. So, for example, it is non-negative, it's monotone, non-decreasing each argument, and is zero whenever the first argument is zero. And this function essentially provides an answer to the question I just mentioned. So whenever the distance between, whenever these three quantities are less or equal than epsilon, the facial residual function provides an upper bound. The facial residual function provides an upper bound to this. Now, it's not completely obvious, but you can show that facial residual functions always exist. So the question is not whether they exist, the question is how to compute them. Now, let me show you two examples of facial residual function. So if K is a symmetric cone, so for example, if K is the cone of positive semi-definite matrices, you can show that for every face F and for every Z in the dual cone of F, there is some constant such that K epsilon plus kappa epsilon plus kappa square root of epsilon norm of X is a facial residual function. So the paper I originally wrote was a bit long, but I would say that around 10 pages was just to prove this, because here we need to use a lot of the theory of Jordan algebra, which is a subject I like very much. But I know it's not everybody's cup of tea. But for example, if K is polyhedral, then the facial residual functions is just kappa epsilon, does not depend on all effects. This is essentially a consequence of Hoffman's lemma. And the thing is that there are some formula for the direct product of amenable cones, and when you have bijective linear images. Now we are almost approaching the main result. So I already talked about amenable cones and facial residual functions. Now I'll show a result that provides a glue to these things. We are back to our feasibility problem. And this result says the following: if the cone is amenable, and you can find some face for which this affine space intersects the relative interior of that face, and that face contains the original feasible region, then you are very close from obtaining an error bound. So he essentially says that if you are epsilon close to the cone and to the affine space, you can bound the distance to the intersection by this quantity, but you have to know how to compute the distance to the span of this special face. So just as a reminder, this problem does not satisfy any assumptions except that it's feasible. And what this result is saying is that if you can find some face that in a sense contains the feasible region, and for which that face you have some constraint qualification, then you are very close from obtaining an error bound for the regional problem. And this is where comes the main idea of the proof strategy. We have the individual distances, and what we do is we find such a face. And once we found such a face, we use the facial residual functions to bound the distance to that face and plug this quantity here. And this will essentially give the kind of error bound we are looking for. Now, how can we find such a face? This is where we're going to use facial reduction. And the very basic idea is the following. we want to find a face that satisfies some constraint qualification and contains the feasible region. So we start with the whole cone. And if the whole cone satisfies our constraint qualification, we are done. If not, if we have this, in fact, there is no intersection with the relative interior, then we invoke a separation theorem that will give us a separating hyperplane. And it turns out that this separating hyperplane, you can use it to go to a smaller face of the cone and then repeat this process. And this is essentially what happens in the facial reduction algorithm proposed originally by Boai and Wolkowitz. And the facial reduction theorem, in a sense, tells you the following, that if the problem is feasible, you can find a chain of faces such that each face is obtained from the previous face by intersecting with some supporting hyperplane. And in the end, you must end up with something that gives us what we want. We get a constraint qualification, and this face contains the original feasible region. Now, you have several choices of this ZI, so you can be efficient or not in this process. And the smallest L is what's called the singularity degree of the problem. Now, in the amenable in the amenable cones paper, I've used a variant of the facial reduction algorithm that takes into account the polyhedral structures, some amount of polyhedrality in the facial structure. But for simplicity's sake, I'm describing here the variant using the classical facial reduction algorithm. So we can just piece everything together and get this main result. But I think everybody might be tired, so I'm just going to show the good parts. So it essentially says the following. So if you have a closed convex amenable cone such that your problem is feasible, then you can find a constant such that whenever you are epsilon close to each individual set, you can upper bound the distance to the intersection by a quantity that depends on the facial residual functions. So this is a special way of composing the facial residual functions. But the point is that this result is sensitive to the regularity properties of the problem. So if your problem already satisfies latest condition, this will give the already satisfied constraint qualification. This will give a Lipschitzian error bound. And if not, you need more regularization steps, and this will be reflected in the final error bound. So this is a result that reflects the regularity properties of the problem. And with that, we can obtain error bound for symmetric cones. So essentially, in summary, if you have K a product of S symmetric cones, then you have N, your problem is feasible. This is essentially saying that you have a uniform Hoderian error bound, and the exponent is given by this quantity. And you also have some upper bounds here that essentially come from the facial reduction algorithm that says how many steps in the worst case do you need in order to complete this procedure. But this exponent is tight because it is tight in the case of the post-semi-definite matrices. So the conclusion so far is this. So if you want to obtain error bounds, this is a possible strategy that you could follow. You first prove that the cone is amenable, then you work out the facial residual functions, and then you apply this result. So some natural questions is, how can you compute the facial residual function? So I only show two examples for the symmetric cones and for polyhedral cones. And what can you do when the cone is non-amenable? So I've been working on these questions with Scott and TK Pong. And some answers to these questions are described in this preprint. And I think I wanted to explain very briefly some of the ideas, but I just want to confirm how much time do I have left?
You have 20 minutes. I mean, you should there are 5 minutes for questions. So.
Okay.
Yeah.
Okay, that definitely be enough. Thank you. Thank you very much. So what we were able to prove is that you can essentially relax the assumption that the cone is amenable, but there is a price, a small price you have to pay for that. And as before, I'm going to keep the details and only show the good parts. So it's possible to prove a very similar result without assuming that the cone is amenable. And a price you have to pay is that the result is a bit less explicit, but you can still get a result following a very similar strategy, which is we apply facial reduction, and then we try to reformulate a problem as an equivalent problem that satisfies a constraint qualification. As we do that, we need to compute the distances to the faces using the facial residual functions, and this gives this kind of a result. But still, if the cone you are working has some degree of amenability, there are a few benefits. But in this work, we had to consider a slightly different notion of amenability, a slightly more broad notion of amenability that we call G amenability. So a function is, a face is G amenable, and G is a monotone non-decreasing function that is 0 at 0. If you get this kind of bound, so for every bounded set, you can find a constant such that you have this kind of error bound. And the thing is that this is useful because if you have two cones that are G amenable, you can use the G amenability to compute the facial residual functions. But the best case is when this G function is just the absolute value function, which recovers the original notion of amenability, which in this case, the facial residual functions for the direct products are essentially just sums of facial residual functions. Another thing you can do with this notion is that it can help you to compute some facial residual functions inside the cone. But I'm going to skip some of these details. Now, the application we had in mind for this project was the exponential cone. So the exponential cone is given by this. Here is a picture of it. And it has a few interesting properties. First, it's not exposed. So because it's not facially exposed, it's not amenable. But still, it has lots of applications. You can see many applications of the exponential cone in this paper. And you can also see some modeling examples in Mosaic's modeling cookbook. Now, what is strange about the facial structure of the exponential cone is this. You have infinitely many one-dimensional faces, and these faces are all amenable. You have two special exposed extreme rays that are the extreme rays corresponding to this 2D flat face. And one of them is not exposed. And you also have a 2D face that is amenable. So this non-exposed extreme ray generates a lot of issues. Now, I'm going to show directly the error bounds we obtain for this. And the result is a bit complicated, but it essentially tells you the following. You have a feasibility problem where the underlying cone is the exponential cone. And you have to take a look at and if this problem does not satisfy a constraint qualification, then one of these faces contains this feasible region and satisfy a constraint qualification. So the kind of error bound that you get depends on the face. So there are two things I would like to draw your attention. So the first is that there is a case where you can show that no Hoderian error bound holds. And there is a second case where you can show that the Hoderian error bound holds, but the best error bound you can get is when you go for something like an entropic error bound. And all of these results are optimal, meaning that for any of these situations, you can find an example of a affine space that when you compute the error bounds, you get back to this case and the inequalities are tied up to a constant. So the message I wanted to tell you at this point is that from the exponential cone, we can obtain sets that do not have a Hoderian error bound. And the concrete example is this: when you pick the exponential cone and you intersect it with this hyperplane. So the system formed by these sets does not have a Hoderian error bound. And this can also be translated in the language of the KL property. So you can use this example, for example, to find a concrete example of a function that does not have a KL exponent. And you can also obtain sets that satisfy Hoderian error bound for every gamma between 0 and 1, but not for gamma equal to 1. And the best case is actually an entropic error bound given by this kind of function. So similarly, you can translate some of these results to the KL property world and obtain a function whose exponent can be arbitrarily close to half, but not half. And the concrete example is this: you pick the exponential cone and you intersect it with this hyperplane. And one thing I forgot to say is that in this paper, there is also some strategies you can use in order to facilitate the computation of these spatial residual functions. But yes, I think that's essentially what I had to talk today. And thank you very much for your attention.
Thank you for your very interesting talk. So if we have comments and questions, just write on the chat or raise your hand. But we have a first comment from Joy Deep. So can you just...
Yeah, hello. Hello. Really nice talk. And what I've observed, if you look into the error bound literature, even the old ones, that on convex inequalities, there are two types. One is where you have inequality constraints. One is the standard Hoffman inequality. But I also have recently a paper with Juan Enrique, which will appear in math programming on error bounds. But So we were trying to actually see that how to take this whole set, basically inequalities and affine equalities and inequalities, everything, and write the error bound. Because for inequalities, you need certain additional conditions, strong Slater condition, etc. How to adjust it with the other part, which appeared that it was not so simple. And because the question, so I tried, the question was again, there were two sets, A and B, and for which you know the error bounds, and then you want to find the distance from the intersection. And I found then we got that paper says we didn't get those results there. Then I worked on it. Then I found the result. I do not know whether you know this result. There's a result by A.J. Hoffman, but he's not this old Hoffman. This is a person from Germany, and he published a paper in '92 where he was showing under what condition I can write the distance of x from the intersection of two convex sets A and B. When a distance of x from A intersection B is less than the distance of x from A plus the distance of x from B with some certain so then I figured out that his conditions, he wrote it in Hilbert spaces, actually quite easily satisfies in most of our cases. So separately, so his results could be applied to actually write down an error bound with the whole set. So I have written down the notes, but I have not yet sent it for publication. If you're interested, I can send it to you. So
yeah, thank you. I'll be happy to. Yeah, I did not know about this, but the kind of situation we are considering, this.
yeah, you also have a similar situation. No? You have you have an intersection of two sets, and then you are trying to. So here also, the inequalities could be representing your, kind of inequality constraints, and the cone could be representing the inequality constraints, and your affine constraints can be represented by this affine space that you are having. So in that sense. Yeah, in that sense, that is why I found little similarity between your work and the notes I made. Maybe I can send it to you.
Yes, I'll be happy. But so in the cases here, typically we don't, the error bounds will typically not be just sums of the individual distances. You
No,
get for their.
I saw that. I saw that. So my question was to write it as sum, so it would be a nice, kind of error bound. But it was, yeah, I could work it out. So I can send you the notes.
Thank you.
Okay.
Do you have any other questions for Bruno? It means while waiting people for the thinking about your talk, I just have a questions. This may not very interesting because you are working with cones and hyperplane. Are you thinking about other like convex set or something? The amenability for a convex set?
Yes. So this was when I worked with Vera and James. We thought about how to extend this notion of amenability to arbitrary convex sets, not just convex cones. This is described. This is described in this paper here. There is some discussion on arbitrary convex sets.
But now, then the result on error bounds is will it still hold or for some cases?
Yeah, that's a good question. So the one of the limitations is that we depend on the facial reduction algorithm, which is it requires you to have a cone somewhere in order to do this process. So when you have a general convex set, it's a bit more complicated to do something similar. So that is a limitation. Of course, if you're of course there are many convex sets. There are many convex sets that can be written as the intersection of a cone with an affine space. And for in particular, if you have any compact convex set, you can construct a cone for it. So you can lift one dimension, construct a cone, and then you can apply this kind of theory to perhaps get some error bounds.
Yeah, I see. Okay. So is there any question and comments for Bruno? So I think we perfectly on time. So thank you very much for your beautiful talk, and thank you everyone for joining the seminars. So we will end this section this week. Thank you, and we will have the next 2 weeks is a seminars, and then we will end season 2 here, and then we will have another seasons hopefully in 2 months. Thank you, everyone.
Thank you very much.
Thank you.
Thank you.
Thank you.